Good day from ChemHelp ASAP. Let's learn a little bit about chemical shift in proton NMR. Chemical shifts vary, but almost every hydrogen we will ever encounter will fall in the range of 0 to 13 ppm. Those are our x-axis values on the screen. Let's start with hydrogens attached to carbons. We can divide these CH hydrogens into two groups based on the hybridization of the carbon. If the carbon is sp3 hybridized, the hydrogen will have a chemical shift of 5 ppm or lower. sp3 CHs are upfield or shielded. If the carbon is sp2 hybridized, the hydrogen will have a chemical shift of 5 ppm or higher. sp2 CHs are downfield or deshielded. Within these broad categories, we have additional regions. For sp3 CHs on the right, if the carbon is only next to more carbons, the H will be in the 1 to 2 ppm range, maybe 1 to 2.5. If the carbon is next to a nitrogen, the electronegativity of the nitrogen polarizes the CN bond, pulls electron density away from the hydrogen, and the H falls more in the 2 to 3 ppm range. If the carbon is next to an oxygen, the H is moved even farther downfield into the 3 to 4 region. These ranges are approximations, so apply them with some flexibility. In general, I like to say that the fancier the environment around the hydrogen, the more it moves downfield. And no, fancy is not a technical term. How about sp2 CHs? Hydrogens off regular alkenes are in the 5 to 6 ppm range. Hydrogens off aromatic rings like benzene are more like 6.5 to 8 ppm. The CH of an aldehyde is normally very close to 10 ppm. What else? Alcohol OH groups can land anywhere from 1 to 5. Amine NHs are more like 1 to 3. Finally, carboxylic OH groups are way downfield in the 10 to 13 range. So that's the OH for an acid. Remember that for our simulated spectra from nmrdb.org, the OH and NHs are not shown. Let's see two examples. The first example is para-tolualdehyde. We'll work from the upfield side on the right and move to the downfield side on the left. The first peak is at about 2.3 ppm. We'd normally think that this is some kind of sp3 CH next to a nitrogen, but in this case the benzene ring next door is pushing the hydrogen downfield a bit beyond its expected 1 to 2 ppm range. This hydrogen is a bit fancier, so it moves a bit downfield. Next we have signals between 7 and 8. Those must be hydrogens on a benzene ring. Finally, we have a nice peak at almost exactly 10 ppm. That is our aldehyde CH. Let's move on. Our second example is 3-amino-1-propanol. The first signal is at 1.8 ppm. That must be an sp3 CH with only carbons next door. Yes, that is the middle carbon. The next signal is at 2.6 ppm. That's an sp3 CH with a nitrogen next door, the CH2 on the left. The last signal is at 3.3 ppm. That's an sp3 CH with an oxygen next door, the CH2 on the right. NMRDB won't show the NH2 or OH. The NH2 could be anywhere from 1 to 3. Let's guess 2.4. The OH could be anywhere from 1 to 5. Let's get 3.5. But it could actually be outside the spectral range that we have on the screen. That's it for predicting chemical shifts. These ranges should be interpreted carefully, but you need not memorize a bunch of chemical shift values to work problems. Just a handful of ranges should cover most common organic molecules.